section 2.6 today after making sure you can put it all together, as in everything that we've done in chapter 2 so far with a problem like this. We're going to make sure that you guys are good before going on to the final section of chapter 2, how to deal with nonlinear inequalities, aka what if you have inequalities with polynomials and rational functions, ending out chapter 2. What to do with inequalities of both polynomials, so what if it's not linear anymore, and rational functions. The final section of chapter 2, the final homework due tomorrow. We'll be reviewing tomorrow for a test on Monday. Here we go. Here we go. It's been on the calendar ever since we started chapter 2. Here we go. Factoring. Woo! Hopefully you guys got x plus 2 times x minus 2 all over x minus 2 times x minus 1. Hopefully. And hopefully in looking at that domain or looking at that denominator, you realize x cannot be either 1 or 2. Hopefully you then went ahead and started thinking about this guy as a function and saying y-intercepts. Isn't that when x equals 0? So hopefully you plugged in and said, okay, what happens if I have 0 plus 2, 0 minus 2, 0 minus 2, and 0 minus 1? Oh, those reduce. Oh, those reduce. We'll get back to that in a second. Final y is negative 2. Hence, we have the point 0, negative 2. Now, it's kind of in my way, so I'm just going to go ahead and stop there. So we have our domain check. We have our factoring check. Okay. X-intercept, this is when y equals 0, right? 0 equals. Some of you guys might have gotten stuck on this, but the only way to proceed is to multiply both sides by the denominator. And what happens when you multiply both sides by x minus 2 and x minus 1? Don't they just poof away? Here's a struggle. Doesn't x minus 2 not exist? Because he's a domain problem? So maybe just multiply an x minus 1 and we get our final x value as negative 2 also. Okay. So, do we have one? Do we have 2? No, we don't have 2. Because who's this guy that we just got rid of? Yeah, it is 2. 2 is the 0, but what kind of discontinuity would he be? A whole, because it would be reduced. If you plugged in 2 up here, it's a 0 over 0. So, 2 is not a vertical asymptote, but what is? Yeah, because that does not remove. Plugged in, it would be a number, 3 over 0. We have a vertical asymptote, and then we could put in parentheses a whole at x equals 2. Actually, we can go even better than that. Now that we've taken away the x minus 2, we could even say where the whole is. It's not just 2. What would the y value be? Plug it in, 4 over 1. We could actually, once you remove the whole, you can look and see, kind of like behind the curtain, Wizard of Oz analogy. You can kind of see, oh, hey, it's at 4 by plugging into what's left. Wait, we haven't talked about wholes a lot, because technically they aren't even really covered in this chapter much. But horizontal asymptotes, yes or no? Tie. What case is it? Top wins, bottom wins, tie? Tie. Since it's a tie, I take the ratio of the leading coefficients. Leading coefficients are these two guys. What's the ratio of the numbers in front? Just 1. Oblique asymptote? None. Why? Adam said it earlier. Say it again, Adam. Yeah, the top. It's a tie. By definition, if you have a horizontal asymptote, and so you're leveling off to one height to either side, there won't be an oblique asymptote. You won't be leveling off to a line. A diagonal line, that's oblique, you'll be leveling off to a horizontal line. If you have one of these, you won't have one of those. But use the clue. The top's not higher by 1. Now, I heard, Tony, you were talking about this with the sign chart. How to make a sign chart. I'm just going to leave that right there. We have to make intervals, right, Tony? Okay. So in our intervals, then we're going to hopefully be able to put it all together in a nice graph right here. In our intervals, we need to be looking at our special x values. There's our intervals. Here's our test x, and here's our test y, basically. Our test f of x. Okay, what intervals do we have that are special x's? Well, what special x's do we have? Let's see. We have a special x at +1 because of our domain. What's going on at +1? A vertical asymptote, right? So 1 is a special x. What else do we have? 2. 2 is a hole, and we can even say where that hole is. 1, 2, 3, 4. So 2 is a special x value. What's another special x value? Oh, here's one. Oh, no, we already have that one. -2. It's an x-intercept. So I have 3 special x values. So that's how I'm going to break up my interval. -∞ to -2, -2 to 1, 1 to 2, and 2 to infinity. Does that make sense? I looked up in all the stuff that we had just done and said, hey, what are special x's? Oh, x is 1, x is 2, x is -2. What's going on there? Oh, he's a point, he's a hole, he's a vertical asymptote. And I split up my number line, -∞ -2, -2, 1, 1, 2, 2, infinity. These are just my pieces. Now I'm going to go kind of quick here because I think you guys are okay with plugging in numbers. -3 looks good, 0 looks nice and easy. 3/2, 1.5, oh well. And then 3. We would have to plug and chug, but did anybody realize that we just made our function a whole lot easier in this step? We just made this function x plus 2 over x minus 1, but I have to maintain the meaning of the whole. I have to say, well, okay, x isn't allowed to be 2, there's a hole, but otherwise it's this guy. That's a lot easier to plug in, because -3 plus 2 is -1, and -3 minus 1 is -4. So that'd be +1, 4. When I plug into my, how would they name this function? In calculus there's a name for it. There might also be a name in pre-cal. Reduced function? No. I'll think of it. Plugging in 0, maybe I'll think of it. You get -2. Plugging in 3, because I'm being lazy and avoiding the hard one. You guys do it too. 5 over 2. Ugh, it's a fraction. All right, 3/2 turn. I'm going to go ahead and rewrite this just to make it easier on my head. I'm going to make it x plus 4/2 all over x minus 2/2. You guys see what I did there? Ah, nice. 3/2 plus 4/2, 7/2. Divided by, which is the same thing as multiplying by the reciprocal of 3/2 minus 2/2 is 1/2. 1/2 flipped is 2 over 1. Oh, hey, this guy's 7. Fractions are not impossible. So I did 3/2 plus 4/2 is 7/2. 3/2 minus 2/2 is 1/2, but I divided by 1/2, which meant I multiplied by its reciprocal. Now all we have to do is say, hey, let's take these points and put them in. So what did we get? We found -3, we found 0, we found +3/2, and then we found 3. All right. -3 is going to be barely positive. Barely, barely. 0 is going to be -2. He's going to be pretty negative. 3/2 is going to be 7. Oh my goodness, he's way up here somewhere. And then 3 is 5/2, which would be 2.5. Oh, what didn't I write yet? My horizontal asymptote at y equals 1. You guys see your graph? Because I do. Let's see how right we are, though. Dun, 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 dun. Done. Well, I just went for what I thought in my head would be easiest. So it has to be a number like on the number line to the left of -2, and I didn't want to do like -2.5 because I avoid fractions. You just saw me do it as much as possible. So I went -3 because I didn't want to go -4 because all of a sudden the numbers get bigger. Does that make sense? So I just went quick, -3. Then this one, I could have done -1. I could have done like a half, but I thought 0 would be really easy to plug in. Then, and actually we already had that number from up here. And then in between here I have to choose a fraction, so I just did 1.5. And then once again, I just went quick and easy. I just went 3. Some people would choose 5 or 10, but all of a sudden you're going to have like weird, like you have to make your graph longer, and I'm lazy. All right, does that sound good? Kim? Okay. I took it from the special x values, which ended up being the domain and the and the x-intercept. So, yeah. Which I graphed, well, I mean, I ended up graphing the y-intercept. It wouldn't have been a big deal. So I wanted to make sure all of this information got over here. So I had to remember my horizontal asymptote. I kind of forgot that for a little bit. I got that in. I did want to get both of these points in, and in doing so, I saw that 1 was an x value. And so I made that, along with my other x's, my guidelines for my intervals. Well, the y is a point. It's just a special point that I can put on the graph. So if it didn't show up here, I would have had another point to kind of guide my sketch. Mm-hmm. Mm-hmm. Because the degrees were tied. Let's get to homework real fast. Guys, can someone find a problem with an oblique asymptote from last night? There had to be at least one. An oblique asymptote from last night. 40, which one? 9, then next page, right? Okay. Here you go, Kim. This one was, these directions were like what we just did. What's the domain? What are the intercepts? Find any asymptotes. Now, I would add in their horizontal asymptote. The book didn't, but I would say horizontal asymptote. In this step, plot any additional solution points as sign chart. This one would have an oblique asymptote because the degree is higher by 1. So we would do long division here. We would do long division here and 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 here. Oh my goodness, they all had oblique asymptotes? Ah, but I would not have done one here. The top doesn't win by 1. I would not have done one. Oh, I would have done one here. Why? You distribute that. Make sense? So if the top is 1 degree higher than the bottom, divide, there will be an oblique asymptote.
So if it's high, then it's none. And if it's 4.8, what will it be? Like the top?
Horizontal asymptote at 0, but the oblique asymptote still none. Yeah. You can't have a horizontal and an oblique at the same time. The function can't be going to a horizontal line and a slanted at the same time. So it's one or the other, or none, or neither. That would be something like, were there any homework? X to the 4th over x squared, that would be neither. Because top wins. Maybe you guys didn't have any of those, though. Probably not. Because those are definitely like have holes or something like that. Guys, let's check homework real fast. Sorry. Number 2 is a vertical asymptote. It doesn't like me right now. Sorry. Leave. Okay. Number 2 is vertical asymptote. Color pens. Homework. Did you have to, well, I don't know. What I care about in number 8 is if you got the answer. Okay, what I care about in number 8 is if you got the answer. Because I showed you a way that you did not have to use a table. You did not have to use your graphing calculator or a graph. So long story short, discontinuities, -2 and 2. Discontinuities, -2 and 2. But the only vertical asymptote should have been -2, right? Oh no, I guess they're both vertical asymptotes. Lo siento. Neither one reduces. So check out the answers. And you need to check, does your notation match the words, or do your words match the words? It depends on how you answered. But as you come towards this vertical asymptote, -2 from the left, f approaches negative infinity, decreases without bound. As x approaches -2 from the right, f of x approaches positive infinity, or increases without bound. The other vertical asymptote, as you come from its left, f of x, once again, negative infinity. As you come from the right, once again, f of x approaches positive infinity. You guys get the difference between, or are you able to compare the words with the notation? Increases f of x positive infinity, decreases f of x is going to negative infinity. Good. Number 12. x does not equal -3/2. Vertical asymptote at -3/2. This looks a lot like one we did yesterday. Looks a lot like one we did yesterday. Vertical asymptote is at -3/2 because remember, you're going to kill kittens or you're going to leave these just as they are. They don't match. Horizontal asymptote, tie, ratio of leading coefficients, -7/2. They say the degrees are equal, I say tie. Same thing. Number 22. Let me give you a second. There was a lot to check on this one, right? Domain, x does not equal 1. X-intercept, 1/3, 0. Y-intercept, 0, 1. Vertical asymptote, at 1. Because those don't reduce. Horizontal asymptote, yep, degrees are tied at 3. You don't have to check their table. It might not be the same as yours. Remember, we have a much better system with our sign chart. Their additional points might not match yours, but the long story short, you should have had your vertical asymptote sketched, your horizontal asymptote sketched. You could have plugged in coming from below the vertical asymptote and coming from above, coming from the left and the right. You would have seen this one going up, but the points kind of indicate that too. The points kind of indicate that too. So maybe you didn't even need to check the behavior. These next ones are really weird because, long story short, the answer key messed up on them, but I fixed them. And I think final answers should be A for 42, C for 43, and B for 44. I don't know if 43 was wrong in the back of the book. Something was off on the answer key with these ones, which is why I typed them out. So A for 42, C for 43, B for 44. 60 was one of the big Mama Bahama ones, right? You guys see that oblique asymptote down there? We'll get to it. There was an oblique. When you did long division, you would have gotten the line 2x minus 1, which is why he, remember, ignore the remainder as our slant asymptote. There was a vertical asymptote. It did not reduce. Some of you might have tried to factor, but it would have been a lot easier just to plug in 2 and realize it's number over 0. Vertical asymptote. You could have tried to find an x-intercept. Where's the x-intercept? What happened when you tried to factor that guy? Modified x method didn't work? No. Quadratic formula didn't work? X equals negative b plus or minus square root b squared minus 4a. What's a? 2? What's c? 5? C all over 2. What's wrong? It's imaginary. Right? No x-intercepts. It does not hit. Negative b plus or minus square root b squared. Oh, I went the wrong way. Thank you. I was trying to remember. It's still imaginary. Minus 4ac. There you go. But doesn't the graph kind of show that too? Once again, your table should be different. Your table should be better than theirs. Maybe some of them are the same, maybe some aren't. Maybe you didn't need to do as many as they did, because there was really only one special x value. I would have just done negative infinity to 3 and then 3 to infinity. Or not 3. What is this? Vertical asymptote? 2. And then I would have graphed my vertical asymptote, my oblique asymptote, and then gotten a couple points and swoop, there it is. Couple points, swoop, there it is. All right. Did you guys get your swoop, swoop? True, true, false for number 80. And that should be our last even. True, true, false. All right. What do we got? Odds or evens? Gavin. That one. Okay. I'm going to pull up the question right here just so that we can peek at it. Some of you guys are checking it, but we'll talk it out. So that's okay. For number 80. Oh, goodness. Years later. Okay. I know I'm being dramatic. Lo siento. Okay. Determine which of the statements about the function is false. Justify your answer. D is the denominator, right? D is the denominator. Question. Why does it make sense that the denominator would be 0 at 1? There's an undefined. Now, could some of you have argued that it could be false and it could be, well, wait a minute, no. I don't know what n is. Actually, I do know what n is. But no matter what, don't I need this to be undefined at 1? Yeah. So that has to be 0, true. Because of the vertical asymptote, I need this guy to be undefined, which only happens at the bottom there. Letter B, the degrees of n and d are equal. Wait, what happens if the degrees are equal if there's a tie? Horizontal asymptote at, not 0, not none, but at a ratio of a leading coefficient. The only time the horizontal asymptote will be somewhere else than 0 or non-existent is when there's a tie. The ratio of the leading coefficients is 1. It's not 1. What's the ratio of the leading coefficients have to be? This one has to be true. There does have to be a tie. The horizontal asymptote is at the ratio of the leading coefficients, but where's the horizontal asymptote? Not at 1, it's at 2. That's false. The horizontal asymptote needs to be at 2, so the ratio of leading coefficients needs to be 2. Only C is false. Yeah, Tony. 19B, what's yours? Okay, so let's go back to 19 first, and then we'll go over to 33. So number 19B, B specifically was finding the intercepts. Number 19 was a bit yucky because he doesn't have a numerator. So intercept, setting, first of all, x equal to 0 for y-intercepts. That one's the one that's not too bad, because then y is equal to negative 1 over 4. Got it? The x-intercept, though, uh-oh. Guys, what happens when we go to solve? What did I tell you about division? What's the only way to deal with it? Multiplication. What happens when you multiply? Anything by 0. Anything times 0 is? And does 0 equal negative 1? No. Which means this graph will never hit the x-axis. Does that make sense? So when you get the impossible statement, it's like, oh, it's not possible to have an x-intercept, so there's none. Robbie, you said 33? Okay, the directions for this one were state the domain intercepts what we just as our opener, right? So for number 33, let's just check some of your math along the way real quick. For those of you guys that did 33 and got it right, can you shout out the factoring? What do we got? All over?
X minus 5, x plus 5.
So I see a whole, right? So this could be the same thing as x plus 5 over x plus 1. But remember, we have to remind ourselves the domain. X can't be 5. So our domain, x isn't allowed to be 5 or negative 1. Our intercepts are y int. We would set x equal to 0, which would be 1. So x equals, setting x equal to 0. Yeah, y equals 5 over 1. Our x-intercept, setting y equal to 0, takes a little more work. So 0 equals x plus 5 over x plus 1. But as we just saw, you can multiply by the denominator to get rid of it to the other side. 0 times anything is 0. So that's going to be, if we were to solve for x, x equals negative 5. Our vertical asymptote is the one that's left over after removing any shared factors, which is going to be x equals negative 1. Horizontal asymptote, what'd you guys get? Yes or no? Ratio of leading coefficients. Good. Y equals 1. Oblique asymptote, yes or no? Come on, opener, you guys got it? No, because the degrees are tied. So oblique asymptote. Oh, they didn't ask for that. Still good to know. And because there's because there's a horizontal asymptote. Good. And then Robbie, the last thing I would do is plot sufficient solution points, which basically just means sign chart. So the sign chart, I would have used the special x's. Kim, does this make sense if I use negative 1 because of this, 5 because of this, And then we also have negative 5. Does that make sense? So we have that one. We have this one. We can actually find our whole real quick. Our whole is at, we could plug in 5, which is 10 over 6. Ew, that's gross. 10/6 would be 5/3. So we could do 5 and then 1, 2 in a little bit. Oops, not open, sorry. Needs to be open, not closed. Whole, 5/3-ish. So then in my sign chart, Robbie, I would have done negative infinity to negative 5. Picked a point somewhere in there. Negative 5 to 1. Sorry, negative 1. Picked a point. Negative 1 to 5. But to save on time, I'm not going to do that right now. I'm going to graph what I know and see if I can at least approximate what's going on. Horizontal asymptote is at 1. Use my trick. Because I could plug in, where's my vertical asymptote? Negative 1. If I plug in negative 0.9 coming from the right, that's going to be a positive over a positive. Oh, this guy's going to positive infinity somehow. Oh, hey, I have a y-intercept too. 0, 1, 2, 3, 4, 5. Should have been a little bit steeper, but there we go. Horizontal asymptote at 1. Good. If I plug in negative 1.1, a negative positive will be a negative. Oh, good. That agrees kind of with what I see. But if you filled out your sign chart, you would have more. So you would see it actually curving up and you would see it curving down with those extra points. Yeah. Yeah. So that one was an intercept. This one I didn't technically show, but that would be an intercept. And then I had my hole. And then I had my swoops. There it is. All right, kiddos. Kyle. Yeah, because we're just matching in those, right? Yeah. All right, last question before we transition over to notes. 42. I see a horizontal asymptote at 0, because the bottom wins. I see a vertical asymptote at 2. And so looking at these guys, seeing if that's enough. These two have vertical asymptotes at 2, so I'm between these two. And, well, they both seem to kind of have horizontal asymptotes at 0. So now maybe I would check the behavior, because this vertical asymptote, they're both going up, and this, they're going opposite directions. I'm going to check the behavior around 2. I'm going to plug in 2.1, which is a positive. So from above, oh, they both do that. They go up. But if I plug in 1.9, this guy goes negative. Ha, he's that one. Does that make sense? At 44, you'll be able to do the exact same trick, but this time they're both going positive. All right, section 2.7. Why, oh why, do I think that we can do this quick? Section 2.7. A, because we're honors, and B, because both polynomials and rationals behave the same way, kind of, with inequalities. You guys saw when we were graphing just now, in the opener and also in grading homework, that there were some special x values when we were graphing rational function. And there are special x values also when we deal with polynomials. Polynomials, the zeros are special. Rational, the zeros and the undefines are special. For polynomials, the zeros, those x values are special. And that's how we would do our intervals for our sign chart. And for rational numbers, as you guys noticed, the intercepts and the domain, aka the zeros and the undefined points, were the special ones. I'm going to call these key numbers. And the long story short for inequalities of functions that aren't quite as nice as just normal linear functions is that we have to make a sign chart, basically, using the key numbers, just like we did for graphs. Except instead of just finding points for our graph, we're going to have to be finding test values to check whether the inequality is true. Test values to see whether the inequality is true or false. as you guys are writing down this page, the example at the very, very top shows us the dilemma. How do we deal with x squared minus x minus 6 less than 0? Right now, we can factor, but what do those factors tell us? We can factor, but what do those factors tell us? They tell us intervals, exactly. What do those factors tell us? Well, they tell us intervals. And basically, according to this page, you can only, because of the intermediate value theorem, a function can only change signs at its key numbers. So I just need to basically test in every interval formed by these key numbers for either function. I just need to test and say, hey, so true or false? Because if one test point's true, the whole interval is true. And if one test point is false, the whole interval is false. And so that's why I'm about to do what I'm about to do to solve this problem. I'm going to do the pages in a little bit different order, just so you can get an example down. So how would we deal with this? Let me show you how I would solve. And the nice thing is, for rational functions, you just have to include zeros and undefined points in your interval, like we practiced today. Our key numbers from this function, because of what we solved over here, are x equals -2 and 3, which is why in our sign chart, when we go to do our intervals, I'm going to go from -infinity to -2, -2 to 3, 3 to infinity. I am going to pick a test x, but this time it's not so much about the y, it's rather true or false with the original inequality. So I'm going to pick test points of, I don't know, -3 sounds good, 0 sounds good, 4 sounds good. If I plug in -3 to my original inequality, which I don't know if I'd plug it in there, I think I'd plug it in the factored form. Might be a little bit easier that way. If I plug in -3, I'm going to end up with -6 times -1, which is going to be a positive number. Is that less than 0? A positive number, +6, is not going to be less than 0, so therefore that guy is false. If I plug in 0, I'm going to get -3 times 2, which is a negative number. Is that less than 0? True. And if I plug in 4, I'm going to get 1 times 6, which is a positive number, not less than 0. False. Guess what? The solution is x is within -2 to 3. Why open? Because it was just less than, not or equal to, the zeros. So kiddos, you might need to get your phone out. This is showing on a graph. You could actually see where the y's are less than also. But I want you guys to get your phone out if you have it. You can also get it on the video or on the notes online. But you might want to take a picture of this page, because this is the steps to solving as to what I just did. See if you can do it in homework tonight. Polynomial rational function. Set up a sign chart with intervals just like we did for graphing, but this time you're taking the test points and plugging into the inequality and saying true or false. False ones aren't the answers, the true ones are. That sounds kind of rational. All right, get out. Get out of here. Bye, guys. See you later. Wasn't even planned. Unintended math pun. It's a good day. Bye, guys.
Go down. Oh, we have a assembly.
Assembly, yes. Go cheer on your homecoming queen.